Welcome everybody back. We are pleased to have Jane Gao from University of Waterloo talking to us about the rank of sparse random matrices. Please.
Thank you, Andrew, for the introduction, and thank you very much for inviting me here for the talk. So I'm going to talk about the rank of sparse random matrices, and also excuse me for the very unprofessional look of my slides. So this is a collaboration with Iyer, Kojagalan, Ergud, Itarich, Mueller, and Robin. So I'm going to talk about three models for random matrices, and just for this talk, I'm just simply going to refer to them as simple models, flexible model version 1, and flexible model version 2. So for the simple model, there are 3 parameters, and positive integer k, positive real number d, and a q as a prime power. And we're going to use the finite field with order q. Okay, so the model is quite simple, as the name suggests. So it's n by n matrix, and for each row, you just independently choose k entries, and for the other entries, you put 0, and for those k entries, you choose non-zero entries from FQ with some prescribed distribution. And in fact, in the whole talk, the distribution doesn't really matter. So for now, we can just assume it's uniformly distributed. And the only thing that we really require here is its permutation invariant. Okay, so that's the model. And for the flexible model, we just change the definition for D and Q, and there's various reasons why we do this. Like in the simple model, we do know that with high probability, you will have columns that are all 0, and there are also columns with a lot of non-zero entries. Typically, there exists a column that the non-zero entries is like of order roughly log n. And for some applications, you just don't really like this kind of matrices. For instance, if you want this matrix to use such matrix for constructing low density parity check code, you probably want there's no non-zero, you don't have any all 0 columns because they don't play any role. So in order to control the profile of the degrees and the profile of the number of non-zero entries in each row, we would like to specify their distribution. And that's the role of the D and the K here. So D and the K are just independent random variables satisfying certain constraints. They just try to bound the tail such that the tail doesn't grow too strong. And then you do want the support of D and support of K to be integers. And then I will just generate n IID copies according to the distribution of D and m IID copies of K. And those D1, Dn will use that to specify the number of non-zero entries in every column. And K's will be the number of non-zero entries in each row. And ideally, I would like to set up in the situation that the expectation of D times n is, roughly speaking, the expectation of the K times m. And that's just because I don't want the event that the summation of all the non-entry zeros in each columns and compare with all the summations of the K wouldn't be, sorry, this event that they are equal wouldn't be too small. The probability of such event wouldn't be too small. Otherwise, I couldn't really successfully get to create such event. Okay, so conditional on such event, then I'm just going to uniformly choose my random matrix where the row J has exactly Kj non-zero entries and the row I has exactly Di non-zero entries. And for the non-zero entry, you choose a random non-zero element from this finite field Fq with some prescribed distribution. So any question about the model? Okay, So for V2, it's exactly the same. The only thing is we don't want to restrict the field to be finite field anymore. You can actually put any general field here. Okay, and here's the result for the rank of such random matrices. So for A from the simple model, we get the rank of matrix A scaled by n. Roughly speaking, it can be expressed by some function that depends on K and D. And I don't really want to write down the function because it probably doesn't really matter so much here how it looks like. And it's just a simplified form from the next slides at a more general form. So for the flexible model where K and D are prescribed random variables, you can write down the probability distribution for random variable D, and I use D of X to denote this generating function, and also the probability generating function for K is denoted by K of X, and then defining this phi of alpha to be, roughly speaking, some compositions of those two functions D and K here, and also involving the expected value of D and expected value of K here, and compose them in a certain way. So the more general form is just that the more general theorem just says that the rank of A from this model, more flexible model, scaled by n, is equal to this formula, 1 minus the supremum of this phi alpha, where alpha is some real number between 0 and 1. So for the simple model, this theorem covers the simple model. So for the simple model, we know the degree distribution. So for D, it's Poisson, and then K is just the constant. It's always 3, so it's a polynomial here for K. And you substitute those functions, specific functions D and K here, and simplify D of X. And then you get to deduce the formula that should be in the previous slide. Okay, so so here's this is equation. The upper bound actually was proved by Lalache like in 2013, and was conjectured to be equation also in the same paper. And we just proved that the lower bound actually matches the upper bound as well.
Jane, can I ask a question?
Yes.
Sometimes, like in coding theory, you like really care about the case of the rank of A being full. Is it possible that you can get at this level of detail, or
yeah?
It's also only about.
In fact, if you really check what this supremum is, in many situations, okay, I will talk about this. Maybe I'll tell a little bit in a bit future slides because
Sure.
it became apparent at that time. Okay, so in the even more flexible model where you don't restrict the field to be finite, then you actually get exactly the same formula here. So this result basically is insensitive to the order of the field. Okay, so here's just a brief review of the literature we know before. So the study of the linear equations, I think in 2002 when Dubois and Mandler, their papers for study of the XOR set, the satisfiability threshold. So so basically the first several papers that I listed here are all for simple models, and they progress in a way that they try to make the model more flexible and cope with more general parameters. So the first paper cares about the special situation where K equals to 3 and Q equals to 2. And it was generalized to any Q greater than 3, but constant. And then it's generalized to situation that the order of finite field can be 3 and 4. So this is the result that I talked before. So we generalize to any finite field and independently, Cooper, Rees, and Pegnan also proved the similar result for the rank of A. Their result is for Q equals to 2 though, but it's also, oops. it works for every density. So D can be anything, even though previously those results typically determines the rank of A at the density of the matrix where it's before the matrix. Stop to become full row rank. So let's maybe speak this way. You can gradually add row one by one, and initially those rows that you add will be all independent, and at a specific value D star, they start to become linearly dependent. And the first few papers over here analyze up to the point of D star, and these papers were able to get results that works for all D. And for the flexible model, I didn't list in this page. So here I just want to quickly mention what is the maxima for this function phi of alpha. There's some conjecture of where actually the maxima would appear. So this phi of alpha is a continuous function. So you take you consider the set of stable points and then just let the row to be the maximum stable points. And it's conjectured and based on the evidence of massive search that in many cases, the supremum of this function actually appears in either at 0 or at the row. So either at the 0 or at the maximum stable point. And at some point it was conjectured that it was always the case. And in fact, it's not really true. So in Lalache's paper, he already realized that there are some constructions where the supremum of alpha actually is strictly away from the maximum stable point. And now we also cook up some other example as well. Okay, so now the question is when, like for what kind of instances you do have the maximum occurring at 0 of row, and for what instances that this inequality becomes strict. And this comes to really understand what this row represents for. And in fact, there's some very natural combinatorial explanations or interpretations for this parameter row. And that comes to the study of the 2-core of this random matrix. So how do you get to the 2-core of the random matrix? You delete all the all the 0 columns, and then you delete a column that has exactly one non-zero entry, like this one, and then the corresponding row, and then repeatedly doing this. So the next round, this one, because this row is deleted, there's exactly only one non-zero entry here, so you delete that column and delete that row. So repeatedly doing this operation, and then you end up with a submatrix that that every column has at least 2 non-zero entries, and that we call the 2-core of this submatrix of this matrix. And then you can get a very trivial upper bound for this rank of A, which is you just counting the number of ones that you encountered in this deletion process. This deletion process basically just corresponds to the Gaussian elimination, and those ones are the pivoting entries. So they count towards to the rank of A, and then the rank of A is simply X plus the rank of this 2-core, which is upper bounded by the minimum between M star and N star. And then you just do some algebraic manipulation, then the rank of A is totally determined by basically the size of M star and N star. And the 2-core of such structure is well studied in random graph theory, and not for this model, but for more general, more special, more unrestricted models. But we can just borrow the arguments there and then prove some results for this A. So work out the size of N star and M star, and then you will get to this formula. And that's exactly what this maximum of those 2 values appearing naturally here. And that holds with this additional constraint that the second derivative of phi at the row is negative. And what it really means that this is negative, it also has some quite nice combinatorial interpretation. Basically, if this second derivative is negative, it corresponds to the 2 core that you constructed is very stable, which means if you just delete a few rows, and then you can keep doing this deletion process, then deleting a few rows wouldn't destroy the 2 core significantly. So after a few more rounds of deletion, you end up with a 2 core that's just having a few less number of rows and columns. And in the other, or maybe the other way to interpret this is that this row corresponds to a fixed point solution in this belief propagation equation. And if this derivative, second derivative, is less than 0, it means this row is stable, is an attractive fixed point. Whereas in the other direction, it is the derivative over there is greater than 1, so it's not going to converge to that point. So, so in that sense, a non-stable 2 core doesn't really predict where the maximum point, where the maxima of the function appears. But if you happen in the case where the 2 core is stable, then typically the rank of A is predicted by, will be given by this formula. Okay, and then you can know that easy calculation would actually show that this whole matrix itself is full row rank in that case, roughly speaking. Okay. Okay, so I just want to quickly say how to determine the rank of A, how the proof works. So the trouble to dealing with this random matrix is it's too restrictive. Like every row and every column, you specify the size specifically. So it's hard to perturb it. So in order to give some kind of flexibility, we delete epsilon and rows from A and then create a new matrix called A epsilon. And of course, deleting just a small fraction of rows wouldn't change the rank significantly. So it reduces to actually study the rank of A epsilon. And using standard concentration inequalities, we know that the rank of A epsilon is concentrated. So it only remains to actually bound the rank of A epsilon. And to do that, we look at the non-space of A epsilon, which is the set of X where AX equal to 0. And that exactly equals to the log of the number of, basically the log of the size of the non-space, taking the base of the log to be Q. That happens when Q is the size of the finite. So this works for the finite field. Okay, so in this non-space, there are two properties that really helps with the proof. One is that we actually know the marginal of a random variable, a random here is really random variable, right? So a random variable nodes. So if you take a random variable nodes and think about the space of the solutions from the non-space, and then you look at the marginal distribution, either that the variable is it takes that particular variable xi takes value 0 in the whole non-space, or it will have the uniform distribution in the finite field FQ, and that's just by the property of linearity. And the second property that's useful is the replica symmetry, or what's called long-range correlation decay. So you take this matrix A and epsilon, and we use Amin's favorite pinning strategy, just pin bounded but sufficiently large number of variables into frozen variables. So roughly speaking, you just add a few rows where you put 1 in those corresponding columns. And that will turn the solution space into a symmetric space, which means if you just randomly pick k variables and look at their joint distribution in the solution space, they form the product rule. Okay, so now how do we get to estimate the expected value of log of z scaled by n? We just use this telescope expansion, and roughly speaking, this quantity expectation of log of z is upper bounded by expectation of the difference between consecutive terms. And then you can use the coupling to couple those two matrices together and then study the log of this ratio. And what only remains to show is this expectation is bounded by the formula that we showed in the first few slides. Okay, so the trick here that it's probably a common trick, but I don't know if maybe everyone already knows. So you started from a and epsilon, and how do you construct the a and plus n+1 epsilon? You basically have to add a new column, a new variable, and then according to the distribution of the neighborhood of this variable, you can generate those rows that are corresponding to the columns here, where those are non-zero entries. But then you perturb the distribution, required distribution for the number of edges too much, and then to make the distribution correct, you have to delete a few rows. Okay, so do it properly. Instead, you can actually delete those rows according to the correct distribution, and then that will be A prime. And then here you just add those column and then rows, and then the A and epsilon would be just adding those deleted rows back, and then you get A and epsilon. And then we just compare the rank between these two matrices and then the difference between here, and then you will basically get the formula you get, right? For instance, if you want to check how this quantity changes if you compare this matrix and that matrix, roughly speaking, it's just taking a uniformly random solution and from this matrix, and then look at the probability that this solution satisfies this set of new constraints. And then you know the distribution of those new rows, those new constraints, so it's easy to actually compute this formula and then taking the expectations. Okay, so the key features here is really you have to you work with this logarithm of this z. Z is a set of solutions, and then you ping variables properly to make the solution space metric. Well, but those all fail if it's not finite field anymore, because you can't really define this log z anymore. It doesn't just make any sense, and then the whole argument seems to fall apart for general field. And the trick here is that you actually work on the rank or the nullity of the matrix directly instead of working on the set of solutions. So I'm cheating a little bit here. Of course, you are still comparing this A with that A prime thing, but to be a little lack of rigorous, I just put AN+1 to be constructed by AN, adding a few rows and a column. So how do we compute the difference between their nullity in expectation? So something that's useful is the following observation. You look at this set of rows here. It's just a few constant number of rows. And the sum of those rows, and look at those columns, they will have a few columns that has non-zero entries. You record those indices. So I is the set of indices for those non-zero columns in B. Okay, and then we say I is a relation for this matrix A here. If you can do linear combination of the rows A here, such that the non-zero entries would coincide exactly with this I. So in that sense, we say I is a relation. And it turns out that if I is not a relation of A and of this matrix, then the nullity is just can be easily computed. The difference of the nullity can be easily computed as 1 minus the rank of this new rows that you added here. Or in other words, those rows that you added here are independent of the rows in this A. So the question is if this matrix A and epsilon does have short relations. The answer is they do have some short relations, but they are not bad ones. So for instance, you may have some frozen variables, and those frozen variables itself forms a relation. But the good thing is we know exactly how many are there. That they are indexed, they are recorded by this parameter alpha. That's the proportion of frozen variables. And then you may have some small relations exist, but then the pinning strategy works here, just as in the finite field case exactly. So if you just ping a large enough number of variables, you kill all those short relations, but those pinning of variables doesn't change the rank much. So once those short relations disappear or become very sparse, that when you add those rows B, C here, it's hardly that I would hit any of those small relations. So they don't contribute much into the final expectation. So therefore, you really only want to worry about the frozen variables, but those are easy to deal with by Gaussian elimination. You just take your BC and look at those columns corresponding to the frozen variables and then turn those entries, those columns into 0 columns. Okay, so now the difference between the nullity is simply 1 minus the rank of B star C, whereas the rank of B star C, you can easily compute using this coupling scheme again. The only thing here is that you generate your B. For instance, this is just B. And now with probability alpha for every non-zero entry, you're just turning it into 0. And then you can compute the rank of those new rows, and that completes. Basically, it's exactly the same formula, same calculation. It's just writing the rank in a different way. Sorry, I ran over time a bit. Thank you.
Okay, any questions?
Yeah, could I ask a question? So the typical rank does not depend on the field, you're saying.
That's right.
At least, divided by n and so on.
Mm-hmm.
But sort of referring to Ryan's question, I guess some of the large deviation probabilities do depend on the field, right? Just like the classic exercise of the probability that a non-sparse random matrix is full rank, right?
Mm-hmm.
So I'm just curious about, since you have this concentration of free energy argument, is it possible to actually calculate large deviation rates for having significantly higher or significantly lower rate? Rank, higher or lower rank?
I think I don't really get what you ask about free energy. What is free energy in this case?
Oh, well, I mean, the free energy is the rank of the null space, right? It's the right. You have this sort of, you might not think of it as a statistical physics style argument, but in some sense, you're saying, well, the number of solutions to the constraint satisfaction problem of being in the null space, the log of that number of solutions is the rank of the null space.
Mm-hmm.
So I'm just curious whether it's possible to sort of, anyway, forget the free energy. I'm just saying that, is it possible to say anything about the exponentially small probabilities of having unusually high or unusually low rank? Can you actually calculate those large deviation rates as a function of the rank?
Oh, I see. You want to see the probability of deviating from the typical rank.
Yeah, maybe that's too much to ask, but I'm just curious.
It's a good
Because
question.
I would expect those rates to depend on the field, even though the typical rank does not.
I guess it depends on the random matrices, right? Sorry, maybe it's the same thing. So it might depend a little. Okay, my guess is it depends on the structure of the two core. At least, you know, the early proof techniques that I saw, they all reduces to the study of the two core, and then they show that the two core has full row rank. And I think it probably has something to do with if you get a typical two core or a very untypical two core. That's my guess, and I think you definitely, so from random graph theory point of view, you do get exponential kind of probability bounds for instance, the two core size is deviating from its typical size.
Right. I guess we know that the two core size has like Gaussian fluctuations, maybe as long as that second derivative is negative.
But I don't know if that immediately tells you something about the rank. But I suspect that maybe the rank does link to the size of the two core, especially. Okay, yeah. I couldn't really answer directly, but that's my guess. If the two core is typical, you probably can show that the rank is full, or is predicted by, you know, the rank of the two core plus whatever you get outside the two core. But if you somehow get a very small two core or something, then you obviously get a rank that's very far from the typical value that you would prove here, and that probability you can bound. But I don't know if the other way is also true. If the rank of the matrix deviates from the typical value, does it actually really must be caused by an atypical two core? I don't know.
Shane, maybe you answered this already and I kind of missed it, but I'll ask anyway. So in some settings of the random variables d and k, like your formula will give that the typical rank is like asymptotic to 1 times n. But do you know any conditions like where that assure you that like the rank will be literally full and not just like full up to little o of n?
Oh, the full rank, yes. Yeah, it's very good. It's very good question. In fact, for all what we can prove, like in the simple model, for instance, even though I said that it takes a value between 0 and 1, right? Oh, sorry, 0 and the row. In fact, for the range of the satisfiability, so I put it in here.
Yeah.
Where is it? So those work where you do for d less than d star, you actually show that they are full row rank, and that's all appearing at the place that the 0 is the maxima. So in some sense, if the 0 is the maxima, it does there is such a correspondence here. And then for more relaxed situation, it's I think if I have to give a conjecture, it's also the case that if the maxima appears at 0 and it's the unique maxima, then you should get the full row rank, even though we do have some technical difficulty to prove it, because of the, if you want to prove full row rank, what's causing the problem here in the proof is you lose the flexibility by deleting epsilon and row.
Right.
And then if you don't delete them, it's very hard to do this kind of coupling procedure,
right.
Because it's very restrictive.
Okay, thanks.
Yeah. But I think there's I at least personally I believe you can basically write the condition that if the maxima is at the 0 and it's the unique one, then I believe it's a full row rank for such random matrices.
Okay.
Any more questions?